Hello everyone, welcome to my Your Programming Club. Today we will be solving another daily LeetCode problem, and the problem's name is number of node good leaf node pairs. Okay, so you will be given the root of a binary tree, and an integer will be given to you, which indicates the maximum distance that can be allowed between a pair of leaf nodes, the binary tree, and those two leaf nodes should not be same. It should not mean that uh, you are choosing the same leaf node and counting its distance from itself, so it will not be allowed. Okay, so the two leaf nodes should be different, and the maximum distance allowed between them is the given integer. Okay, and so this kind, if the distance between two leaf nodes is less than or equal to the maximum distance allowed between them, then they are called good pairs. Okay, so you have to find the number of such good pairs. Okay, good leaf node pairs, you can say. Okay, so let's see how we can do that. Before thinking of an approach, let's have a quick look at the constraints also. So according to the constraints, the number of nodes in the tree is of range 1 to 2 raised to power 10. Okay, and the node value will be ranging from 1 to 100, and the distance between the maximum distance allowed will be order of 10. Okay, so let's try to think of an approach. So let's take the first example to the board and try to understand how we can solve it. So as you can see, you were allowed maximum distance of 3. Okay, so the distance limit that was given to you was, just a second, 3. So distance limit is 3, and the leaf nodes are these 4 and 3, and the distance between them is the number of edges that are required to traverse, so it is 3. So we can say that we are having one such good pair. Okay, so as you can see, the answer is 1, but the question arises that how we can do so programmatically. So as you can see here, if somehow we know that how many number of leaf nodes are there on the left hand side of one, left hand side leaf nodes. Okay, and their distances, okay, from 1. Why we are choosing only 1? Because 1 is the least common ancestor of these two leaf nodes, 3 and 4. So least common ancestor. So what does it mean by the least common ancestor? So when you go up to the parents of these leaf nodes, so this is a parent, or you can say ancestor, and this is also ancestor. So 2 is ancestor of 4, 1 is ancestor of 4. Okay, here 3 was having only one ancestor, which was only 1. Okay, so what is the least common? Least common is meaning that which is the ancestor that is common to both of these nodes, and is at the minimum distance from them. Okay, so it is 1 indeed. So that's why we will say it is the least common ancestor. Or there might have been a case that, let's say, this tree is even extending further. Okay, so let's say the tree is something like this. Okay, so this would also have been a common ancestor of both of these 3 and 4, because they are sharing it, but it is not from both of them, it is not minimum distance possible. So that's why the term the least common ancestor. I hope it's now clear to you what's least common ancestor is. So at each least common ancestor, you would be wanting to find out the left hand side leaf nodes and their distances from that ancestor or the current node. Okay, so this is the current node, or you can say possible ancestor of leaf nodes. Okay, and then once you are having the number of leaf nodes and their distances from current node. Okay, and from right hand side also you would be wanting that you would be having something similar, which is right hand side leaf nodes and their distances from current node. Okay, if you are having all these things, then you can form pairs. Okay, so you can cross multiply and check whether we are, let's say, what we can do here is we can use a array. Okay, since it was mentioned that in the constraints that distances will be at max 10. Okay, so we can use a 10 size array. Okay, so you can use a 10 size array from 0 to 10, indicating the distances. So these indices indicate distances of nodes. Okay, from current node obviously. And why we are only storing only distances till 10? Because it is the maximum limit of the allowed distances value, or the distance limit, you can say. Okay, so the question arises, there might be some good pairs down the left hand side or right hand side, or left subtree or right subtree. Okay, so there might be some good pairs here also. Let's say it was something like 0. Okay, so as you can see, these two are forming good pair, but one is not having any information about such good pair. So in order to include the number of good pairs on the left subtree and the right subtree, we increase our array size by 1. Okay, so instead of 10 we take a size of 11. So this 11th or the entry, what it will do, it will store the number of good pairs in the current subtree, the number of good pairs in the current subtree at current node. Okay, or till current node, you can say. Till current node. And how are we forming the pairs? We are forming the pairs bottom way up. Okay, with the help of this concept LCA, we will be forming the pairs bottom way up. Okay, so this array will give two kind of informations. The first information is the distance of each node from the current node, each leaf node from the current node. Okay, so let's change the slide and see what the array will give us. So the distance of each node from each leaf node, basically from current node. Okay, and the second thing that it will give is the number of good pairs already formed before reaching current node. Okay, so these two informations will be given to us. So it will be nothing but the 11th entry, and this will be from 0 to 10 entries. Okay, in the array that we are talking about. And then once we are having all these, we can have a cross multiplication and form the number of good pairs from the by matching a number of good pairs from left and right. But a condition that should be satisfied is that the distance of leaf node on, let's change the color here, the distance of leaf node on left side plus the distance of leaf node on right side, both of these from current node, or of left side and right side of current node. Okay, plus 2. Why we are adding 2? Because let's say that this is the current node and you are having some leaves here. So let's mark the leaves. So you are having two leaves here. So you can see, but the distance of these two leaf nodes, we should also include these two edges. Okay, which we have not done. So in order to include these two edges or count these two edges, we are adding 2. Okay, should be less than or equal to the distance limit. Okay, or the given distance variable. I am calling this distance limit. Okay, if this condition is satisfying, then it will be counted as a good pair. Okay, so this is how things will proceed. And on top of that, after, let's say, we have, or I think it is a good time to bring the implementation here, so that we will be spending less time and it will be a little bit easier for me to make you further explanation of the algorithm. So let's bring the code to the board. So this is the code. So then what we will be doing is, since you can see that, let's change the slide. Let's take a new slide. So if there are some leaf nodes down here and we are moving up in the tree. Okay, so let's call this leaf 1, let's call this leaf 2. So leaf 2 and leaf 1 both were at a distance of 2 and 2, 1 and 1 from the current node. But when we reached this node, which is the parent of the current node, our distance is increased by 1. Okay, so one level is again added because of the this node. So when we will be at this node, both of the leaf nodes will be at a distance of 2 and 2. Okay, So in order to make this addition possible, what we will do is we will simply increase the distances of the nodes. So each entry will be moving one step further, one step further, one step further, because these indices indicate the distances of node from the current node. So each entry will be shifted towards the right. Okay, so once we have done it, then we can count the nodes. So let's see how things are going on according to the code, otherwise it will be a little bit confusing for you and it will be harder for me to make you understand also. So as we talked about, we will be using a 12 size array. Okay, so from 0 to 10 it will be storing distances from current node, and on the 11th index this array will be storing number of good pairs till now, till current node. Okay, so if the we are doing we will be doing a simple DFS call, and this count pairs helper function will be returning an array. So array will be of size 12 as we have already discussed. So if first of all we will declare a 12 size array, and this 12 size array is named distance node count map. So the distances and the number of nodes which are at such distances from the current node. Okay, so if the current node is null, it means that there is no node here, so you will return the empty array indicating that okay, there were no nodes at any distance from the current node, because the current node is itself null. But if the current node is a leaf node, if current node is leaf, then in that case you will say that the current node, which is the leaf node, is at zero distance from itself. Okay, current node at zero distance from itself. Okay, and then you will return the distance node array. Okay, indicating the leaf node. So because you have to start somewhere if we want to store these entries also in the array. So these entries are at a distance of 0 from itself, because we are counting the distance of the current node from the leaf node. Okay, so that's why. So now moving further, then you will do a post order traversal. First of all, you will be, as I talked about, that we need to find this. We are considering each node as a possible LCA, each node as a possible LCA, least common ancestor. I hope it is clear to you what a least common ancestor is. So each node is considered as a possible LCA. That's why we need to have information about its left subtrees and right subtrees. So in order to do so, we are doing here a post order traversal. Okay, post order traversal. Those of you who are hearing this term for the very first time, it is nothing but we will recurse for the left and right subtrees first, and then we will be checking for doing computations for the current node. Okay, so you will be getting those two arrays for the left and right subtrees, and as I already told you, that these two arrays will be storing two informations: the distance of each node from the each leaf node from the current node, which the current node is basically considered to be a possible least common ancestor. Okay, and number of good pairs that have already been formed before reaching the current node, since we are forming the good pairs in bottom way up. Okay, because of use of this recursion in the manner we are using it. Okay, so once we have done all this, then we are having that information, and first of all we will be finding out the number of total good pairs till now, which will be nothing but the sum of the good pairs till now in the left subtree and the number of good pairs till now in the right subtree. Okay, which will be stored at the 11th index, as we already talked about. Okay, of the arrays that will be returning by the recursive call of left and right subtrees. Okay, and then as we talked about that, since we are moving at one level up, so we need to increase all the distances of all the leaf nodes by one. Okay, increase distances of all leaf nodes by one. Okay, and since after the current node, let's draw a tree here. So after the current node, let's say these were the two leaf nodes. After the current node, the number of leaf nodes for this particular node will be the sum of these two. Okay, so in order to do that, we are adding the number of leaf nodes at the current distance on the left subtree, and as well as the number of leaf nodes on the right subtree at the current distance, and we are increasing its distance by one or adding one distance to it because of the current node. Okay, so it will increase one level. Okay, that's what we are doing here, and then we are trying to form the number of good pairs considering the current node as a LCA, possible LCA. Okay, so considering current node as possible LCA, considering current node as a possible LCA. Okay, so we are considering that this node might be a merge point of, you know, the leaf node information coming from both directions, from the left and right directions. Okay, so we are checking the pairs of distances that can be there. So each node, each leaf node on the left and right side must be at some distance from the current node. So we are checking all those pairs, and for those pairs we are checking the distance. We are having a nested loop kind of situation, and as I already talked about, for the condition check, this 2 is for the both of the edges, so these edges being not counted in the distance, and it should be well within the distance limit. If the condition is satisfied, then we will say that okay, uh, whatever the number of nodes were at these two distances, distance 1 and 2 in the left and right subtrees respectively, just multiply them and add the number of good pairs to the 11th index for the current node. Okay, so it will indicate the number of good pairs, and for the current node you will be returning the array that we talked about, the distance node count map. Okay, for each node you will be returning so, and root will also return such kind of array. So for root, if you access the 11th index, so it will be having the total number of good pairs in the entire tree. Okay, so this will return your answer. So I hope you are able to understand the approach and the intuition behind it, and if you are still having any kind of doubts or any queries in general, so you can ask them in the comment section. And before ending the video, let's have a quick discussion on the time and space complexities also. So time complexity wise, it is order of n, since we are visiting n is the number of nodes, since we are visiting each node at least once, and we are also doing a nested loop here. So let's change the color a little bit so that it can be visible to you. So we are doing here a nested call. So it will be nothing but, since we are considering the maximum distance limit, so distance limit square. Okay. So although it is 10, but n into distance limit square. So that's why we are considering the time complexity to be this. And for the space complexity, as you must have guessed that it will be the height of the binary tree. So order of height of tree, because of recursion call stack. Okay. In the DFS call that we just made, so this if you are not familiar with this kind of traversal, this is just a DFS traversal of a tree, depth first search. And if you are hearing this for the very first time, then a link will be there in the description for DFS article explaining what DFS is. And now moving further, and you might think that why we are not counting these three arrays that we have declared for the left and right subtrees, and one for the current node, this array. You can see that we these arrays will be having a constant size irrespective of the nodes. Okay, so that's why we are not counting it. Otherwise, so you can say the overall time complexity will be height of or 3, the space complexity, sorry. And so these are the complexities. So as I said earlier, if you are still having any doubts, feel free to use the comment section. And I really hope this solution walkthrough added some value to your journey of honing your DSA skills. And I will see you in the next video. Till then, keep solving more and more problems. Thank you for watching.